hopefully on number 1A you use the z-score of 1.96. So you gotta look at 0.025. Or you look at the little baby one, but be careful you look at the right side. This side just tells you the area below the z-score of 1.645 is 95. That's what that is. Because that's what this chart tells you, the area below z-scores. This one tells me what z-scores have 95% between them. Negative 196 and 196, that's why I gotta use this. Or if you look up 0.025, the closest I get from 0.025 is somewhere there. It's exactly 0.025. 1.96. Cool. Fine. So you guys are the very first one, this is what they get for the confidence interval. I get 67.59 up to 69.21. Cool. All right, I'll let you.
They're giving you what areas you want to have. I think we are. I just thought you were trying to find.
So we are 95% confident that the interval 67.59 to 69.21 inches contains the true mean height of men. Little known sequel to the city of men, the true mean height of men. So this one, what some of you guys realized, some of you guys did this, you put in there 1.96, which is good. You put in there 2.5, which is good. And then on the bottom you put 0.80, whatever you got. And of course n came out to be 37 because I already knew for a sample size of 37 I'm going to get this error. That's not what I'm asking. I'm asking, I want to be within 0.5, not within 0.8. So if I want to improve my error, would I have to take a larger sample or a smaller sample? Larger. So if I put a 0.5 down here squared, well, yeah, 0.6 squared, 0.6 squared, I get 96.04, and I know that's really, really tiny. I don't care. You round up to 97. Now, real quick, how many men did I already talk to or measure? How many men do I have in my sample already? 37. So how many more men do I need? 60. All right. So just in case I ask for how many more men would you need, You just subtract the number you already talked to. I like it. So I've been known to ask that kind of question.
97.
Basically going to a coma. I'll see you guys next week.
It's nice when you can have a control to come. As long as you're able to come out of it at will.
Set up a computer gold machine to go on 6 hours.
You watch Mythbusters?
Yeah.
They had that whole episode where they had a bunch of, where they tried to create this computer gold machine. It was comical on all the times they didn't quite look right.
It's something about
Everybody has
Oh, that's fine.
Alright guys, let me catch up to you on this second part. So P hat would be the 316 out of 652. If you do that, no Jeff, I get 0.485. So what's Q hat going to be?
515.
Good, 0.515. And N, of course, is what? So many people make the mistake of that. Be careful. It's the bigger one. Don't be doing that. That was a little extreme. Shit, you picked the appropriate level of cuss word. That was a shit. All right. Who remembers, why would this be sitting here? What's that all about, this thing?
Oh, it's the same word as
Yeah, I'm not allowed to use z-scores unless this thing is normal, and it's got to be bigger than 5. So what's n times p hat? Now the funny thing about this, how did we calculate p hat? We did x divided by n. Now x is the number of successes, and n was the total. So what's n times p hat going to be? It's going to be frickin' x. It's going to be 316. Now if you want to take the time and multiply it out, feel free. Depending on how much you rounded, this will be 316. That's bigger than 5. And this will be the rest. This will be 336. That's bigger than 5. So if you actually do 652 times 0.515, you'll get 336 times 0.485, you get 366. They are both obviously bigger than 5. So this is normal enough. I'm allowed to use z-scores. Cool. So for 91% confidence, how much is going to be just on this side? 0.45, because there's 9% outside, so there's 0.45 on that one side. If I look up 0.45, the closest I can get is actually here. 170.
169.
No, 169 is 5 away. 170 is 4 away. Nah. Sorry. So there'll be a little bit. I'll give you some leeway on that. It's not a crazy huge deal, but try to get as close as you can. So it's negative 1717. So it's just 170 I can put in for a z-score, 1.7. So now I just plug and chug. I've got 0.485, give or take, 1.7 times the square root, 0.485 times 0.515 divided by 652. Whew. So one thing that I understand when you're a student that's not taking a lot of math, you can very easily lose connection between why this formula works, and then you start just seeing it as I'm just doing a bunch of shit to numbers. But remember, we actually developed this formula. We created it based on things we already knew. So we understand why this formula works. Yes?
For the z-score, we got 1.75. Did you mark that wrong in the test?
That's way too far away. 1.75 has an area of 0.04, which is not enough. That would be related to 92% confidence interval. 92% would have 8, 4% on one side. 91 has 9% outside, 4.5% on one side. So it should be 0.045 you're looking at, not just 0.04. I like it. Where are we at? So now we can do 1.7 times the square root. 0.485, yeah, root. Square root. I get this. See, I got the new calculator. It's got the big old square root.
That's just the error.
That's just the error. I like it. So it'll be 0.485, give or take 0.03333, I guess. 0333. What's up?
Got 0.3.
3. I don't know what to tell you. Did you put that in there?
Just different. Because I had to I have to do it parts because I don't know if my calculator works.
Oh, it does. They know order upper. Even if
It said error before when I've done it like that, so I just do it in small chunks.
Oh, okay. But something, be careful. If it comes out right, then I'm okay with that. Alright. And unfortunately, I don't know when it's right. Well. So what do you get for the interval when you do this?
0.4517 and 0.5183.
So we are 91% confident that the interval 45.17% to 51.83% contains the true percentage of people in Wisconsin who voted. Peep who vote. Peep of Pope. The percentage of the Pope that voted. Percentage of pebbles that voted. All right. Now here's the part that I was hoping somebody would wonder where the hell that came from. Where the hell did that come from? Probably the same place the other one came from. Right? If I take the error to be this piece of it, and I solve for n, so I can square everything, and then I can multiply the n up and divide the e down, I get n equals z squared p hat q hat over e squared. That's the formula. It's the same way we got the other n. So now I just got to plug and chug. I got z is 1.7. P hat was 0.45. Q hat was 0.515. E, what do I want E to be? Yeah, within 2%. So up here it took 652 to get within 3 1/3% almost. So I'm going to have to take a lot more than 652 to get it all the way down to 2%. So if I put 0.02, be careful, don't just put 2 down here, put 0.02 squared. 2% ain't a number. 0.02 is the number. Ain't a word, I don't care. 1.7 squared times 0.485 times 0.515 divided by 0.02 squared. What do you guys get for that?
1804.
Yeah, 1804 point blah, so you go up to 1805. Sounds really Actually, probably back. A lot of bad stuff. All right. So, any questions from that handout? There. Don't worry about the other side yet. It won't make any sense yet. Yes. Just want to see if there's any questions. Everybody cool with that so far? Okay. Okay. All right. So last bit for today. See how much more this guy could take. Little great boy coming over. Get out of here! Oh, stop! I just want to see someone pushing him out with a broom. Get out of here! Take that stuff somewhere else. All right. Yes. So now we're coming back to A2. So just remind you, we just did this one. Everybody. Every single person. Hello. We just did this one here. Hey, that means shut up. That's what that means. We just did this one here. And we did this one before. These are all confidence intervals. You can tell the confidence intervals because the plus or minus kind of gives it away. All right, so when I ask you to construct a confidence interval in a test, you're going to look on your formula sheet for these. All right, so there's going to be one more confidence interval we're going to put up here, one more formula we're going to put up here. And that's if I don't know this. So if there was anything in my confidence, I construct a confidence interval, but then I go, oh, I wasn't really sure about this piece of it. Should I make it bigger or smaller because of that? Good. Bigger. So anything that I'm not sure about should make my confidence interval bigger to, again, cover my ass for the thing I don't know. So if I know this, I can use the z-score that tells me how wide the confidence interval is going to be. If I don't know this, then all my confidence intervals should be a little bit bigger. In fact, if I take a sample size n, and I get a standard deviation for the sample, and I want to use that as an estimate for what this is. As my sample size gets bigger, am I going to be more or less sure about that estimate? As my sample size gets bigger, I'm going to be more sure about this. So therefore, the smaller my confidence interval can get. So anytime I get my sample to grow, to be bigger and bigger and bigger, then I am more and more certain about what I see. My confidence interval should get smaller. So I want to use something in place of z that's always a little bigger than z to cover my ass because I don't know sigma anymore. But as n gets bigger, it gets smaller. Okay. So we're not going to have to calculate this. And this part is not going to be the best thing you've ever heard either. It's going to be a whole other chart. But it's instead of looking at the z-score chart, I'm going to look at what's called the t-score chart. I always want to see what kind of... Oh, I love it. You guys are like, what the? I just got used to the z. Well, good. It's the perfect time to do another one. A little history. Any guys drink Guinness? Any guys drink Guinness at all? Yeah. All right. The person who invented the T-scores, he worked for Guinness. And he was doing some analysis on how to make sure that their stout was in the appropriate range, right? So he was trying to figure out some statistical analysis that he could do. And he came up with this T-score test. Because he didn't know the standard deviation. He didn't know all of it. He could just take samples. So he only ever had the sample standard. He only ever had S, not sigma. So he had to call it, though, he had to call it the student T distribution because he wasn't allowed to publish his findings because it was company rules that he couldn't publish his findings. So he had to give himself a pseudonym. All right. So that's kind of the history behind it. It was constructed to analyze Guinness. So that sort of brings more people in normally, I find. So that's interesting. I don't have Guinness for us to drink. I'm sorry. So if you came back for that, you can bring some. Well, don't bring some next time. It's probably not good. Don't do that. So now, without even showing you yet, but what's going to happen here is this is going to let this be remarkably beautiful. If I know S, but I don't know sigma, I must use a t-score. So that's going to be another formula on your formula sheet. So if you're like, oh, do I use a t-score here? Well, the formula sheet tells you, well, if you know sigma, you use Z. If you know S, you use T. In fact, t-scores were invented to cover our ass for when we don't know the true standard deviation. We only have a sample standard deviation estimate. That's why they were invented. Let that be unbelievably nice. All right, maybe. Yes?
So you said S is the estimate for the standard deviation?
Yes, S comes from the sample. So it's always going to be an estimate. Sigma. Just like X bar, I expect it to be close to the mean, but it estimates the mean. It's never going to be exactly mu. Well, you know, I put my money on it not being mu, but it estimates mu. If I take a good random sample, that should be close to this, that should be close to this.
Gotcha.
But it won't be exactly the same. I like it. All right, so, two things. One thing is this. Let me talk about this by itself. There's an idea called degrees of freedom. So go with me here for a second. If I told you, now just go with me. This is related. This is how we got to know this idea to use the chart to find the t-score to make this confidence interval. Oh shit! So let's just analyze this idea by itself for a second. If I told you I had four numbers that average to be 10, is there any of those numbers? Do you know anything about each number individually, if they average to be 10? Each of them could be something entirely. Could any of them be a billion? Of course, as long as another one was like negative a billion, and then the other two are 10, or 10 and 20 or something. As long as it adds up to be what? If four numbers average to be 10, they have to add up to be 40. I love it, because if you take 40 divided by 4, you get 10. So four numbers have to add to be 40 to average to be 10. So how many numbers can I just totally make up before I have to really buckle myself down and make it work? So I can make the first one anything I want to. 17. I can make the next one 28. I can make the next one 7. Can I make the last one anything I want it to be?
No.
I can't, because I have to have it add to be 40, don't I?
Yeah.
So the last one in this case would be what? What do I have so far? 52, so the last one actually has to be negative 12. So how much freedom did I have? Did I have 4 degrees of freedom up here? What's your gut tell you? No, I had 3. So in fact, degrees of freedom is always n minus 1. Because you always have that many things you can make whatever the hell you want it to be, and then the last one has to be the thing that make it work. So the idea of degrees of freedom is actually independent of statistics. It's just how many things can you make up until you have to make something make it work. So this will be n minus 1 in general. In this case, it would be 4 minus 1 equals 3, because I could make those 3 numbers whatever the hell I wanted them to be. So, second thing is to use Z or T, we must have a normal distribution. So if we offered a stats 2 here, that's where you'd start learning what to do if it's not normal. Right? The first level stats, we do a lot of, well, if it's normal, if it's normal enough, if you check it and it's normal enough, this is what you do. And the second level would be, oh shit, it's not normal enough. Now what the hell do you do? We don't though, sorry. Alright, so here's what's going to happen. Let me give you this, and then we'll talk about how to read this, and then I'll unleash you on the back side of this conference, and we'll hand out. Yes, this is one more chart. You're responsible for it. Don't write on this any notes. Bring it with you to tests. All that kind of stuff.